Calculus. Welcome back to Luke's Math. So we didn't have a problem to go over last video, so today we're just going to start with a definition, because today's topic is on independence. So let's define what makes events independent. Okay, so we have the first definition, and this is for independence. Okay, so we say two events, A and B, are independent um, independent they're independent events specifically if one thing is true. If we know that the probability of A intersect B is equal to the probability of A times the probability of B. Okay, and then we say otherwise A, B are dependent. And so this is a good, reliable way to check. Okay, do we have independent events, or are they reliant on one another? Okay, so let's do a quick example just to highlight how we do that check. So for a quick example, let's say we have that the probability of A is equal to 1 over 6, and the probability of B is equal to 1 over 4. Then the probability of A intersect B is equal to 1 over 12. And so in this case, they are not independent, since the probability, since we have that the probability of A times the probability of B, that's equal to 1 over 24, right? That's not equal to the probability of A intersect B. Okay, quick example highlighting it. Now we have a theorem as it relates. This one should be, this is why it's sometimes relevant to talk about independent events. So if the, let me write this in black, sorry. So if the probability, making a lot of mistakes, the probability of A and the probability of B are both greater than 0, then A and B are independent if and only if either of the two statements I'm about to write hold. And so we need either that the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. And I'll give a quick demonstration to show why we know that needs to be true, right? Because the probability of A given B, by the definition of conditional probability, it's the probability of the intersection over the probability of B. And so we said if they're independent, well then the intersection is just the product of the probabilities of both of the elementary events divided by the probability of B, which we said was not equal to 0, so they cancel and we're left with just the probability of A. Okay. Next, we have another theorem to go over. This theorem has 3 results, and we can prove, since we'll have time, I'll prove the first result of this one. Maybe on your own, try to consider how you would do the proofs of the other two. They're similar. So we have if A and B are independent, then three results. The first result, A and B complement are also independent. A complement and B are independent, and A complement and B complement are both independent. And so, all right, are also independent. Okay, so that's an interesting result. We get just that the two main events are independent, and then we can say any sort of combination of those events and their complements are also independent. Okay, so let's do the proof. And this is just the proof of 1. So we know that the probability of A, sometimes let's partition the set A. So if we partition it, we can write it as the union of two disjoint sets, right? So we know that the probability of A is equal to, when we want to partition A, we can write it as A and B, or A and B complement. So that's like in the Venn diagram, that's like partitioning it to this one, and then this one separately. We're just unioning those together. So those are two disjoint sets, meaning if they're disjoint, they're mutually exclusive, right? So the union of those two should just be the sum of the probabilities. Okay, let's keep it going. So we have the probability of A times the probability of B plus the probability of A intersect B complement, right? Because they're independent, so the intersection is just the product of the two elementary. But right here, if we rearrange stuff, we know that the probability of, let's rearrange our equation, we get the probability of A and B complement is equal to the probability of A minus the probability of A times the probability of B. Okay, we can factor out a probability of A, and if we have 1 minus the probability of B, well, what is that? That's just B complement, right? And so what we'll get is the probability of A times the probability of B complement. And so if these two are equal right here, well, that's the definition of independence, so we're done. We know that A and B complement are independent. Okay, so maybe try that, the proof for the other two consequences of that theorem. But now we should talk about another definition. Okay, and this is naturally, it's like we talked about, when we have two events that are mutually exclusive, how do we, you know, generalize those results to a finite, say, number of events. It's the same process now. So we have a finite collection of events. So events A1 through K are independent. This is going to be a weird way of writing it, but it'll make more sense hopefully after I explain it. So if for all j equaling 2, we start the index of j at 2. So we have to put the k there, we go to k. Okay. And every subset of indices, so we start at I1 is a subset of indices to ij, then we have the probability of the union of all of those. sorry, the intersection, that's not the union, the intersection of all of those is equal to the product of each probability of the specific events. And then it would be dot 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 times the probability of Aij, right? Okay, and essentially what this is saying is any sort of combination, any sort of subset that we can come up of events, they themselves have to be independent, right? In order for all the events to be independent. So any two common events have to be pairwise independent. Well, as well as like if we take 3 events, they also have to be independent. 4 events, they also have to be independent. It's just a way of sort of saying that, communicating that idea. And so we talked about what about just 2 events, right? So we can let's rewrite the definition for pairwise independence, right? So if we have multiple events to choose from, so the events A1 through AK are pairwise independent if for, let's write our indices, so for I going from, or let's get 2 indices, we'll need 2. So we have 2 indices, I and then J are natural numbers up to K. Then the probability of A, so choose some random event AI and then another random event AJ. Those 2 must be independent for any I and J as long as those I and J aren't the same, right? So for we choose 2 random events as long as those are independent, then every event is going to be pairwise independent for if we do it for every single one, right? So for as negative, it's J. Okay. However, here's the thing. These 2 definitions that we wrote are not the same, right? So we can say that events are pairwise independent if 2 events that we choose, any 2 events that we choose, they themselves are independent. But that doesn't necessarily imply that all events, that makes that all of our events are in general independent. So let's do an example, a really nice example, actually, I think, that highlights this this difference between the definitions. So we're going to describe the sample space to be the unit square on the Cartesian plane. Okay, so what does this look like? This is a 1 by 1 square in the first quadrant of the Cartesian plane. So this would be the sample space. And then I'm not going to write this down because I'm not sure. I'll just verbally state it. We're going to describe the probabilities of each outcome or each event here as just the area within the Cartesian plane. So in this case, what is the area of the sample space? Well, it's just 1. It's a unit square. Okay. Now let's write out a couple events. So let's say that A1 is this rectangle. I'm not going to verbally state it because it would get complicated, but it's this sort of rectangle. A2 is another rectangle. And then A3 is going to be a weird shape. It's going to be kind of 2 distinct disjoint sets within the unit square that we've drawn. So we have 1 square right here, and we have another square that's going to be disjoint from that. Well, I guess they're not entirely disjoint because they're going to share 1/2 in common. Okay, so let's just draw out all 3 of these regions just so we're on the same page. So This will be A1. Here's our unit square. A1 is this region, the left half of it. A2 is this region, the bottom half of it. And then A3 is the weird sort of two squares that we have going on. It's the bottom left corner and the upper right corner. So hopefully you can see that for any of these events, what is the probability? So for some arbitrary one, any of these events, its probability is 1/2, right? Because it's exactly, all these areas are 1/2 of the total area of S of the sample space. Okay, now let's do some work with independence. So if we say that the probability, let's take two events. How about A1 and A2? We're going to find the intersection. Well, the intersection is that little square in the bottom right half. So that's going to be 1/4, right? And these are independent because we know that for each individual event, the probability is 1/2. So this is also equal to 1/2 times 1/2. So these are pairwise independent. In fact, we can say that any two of these events, any two combinations are pairwise independent. So we'll say because if you take any two events, arbitrary events, so AI and then some AJ, intersect them, we're going to get 1/4 as the probability. And then since each of them are 1/2, right, so the probability of AI times the probability of AJ, since they're both equal to 1/2, 1/2 times 1/2 is equal to 1/4, so they are independent. So we say, let me write that actually formally. So A1, A2, A3 are pairwise independent. However, this agrees with our definition of pairwise independence, but what about the other definition that we came up with? What is the probability of the intersection of all three events? Well, the intersection is that bottom left square, so it's just going to be 1/4, right? This is the region we're looking at. And it's a 1/4 area. But if we take the probability of each individual events, that's 1/2 cubed, right? So which is 1/8. 1/8. And since these are not equal to each other, we can't say the events are independent. They're pairwise independent, but not independent. So events, A1, A2, A3 are not independent. Okay, that's all I have for today's lesson. But we do have an exercise for today that I can go over with you all tomorrow. Okay, so here's the exercise that I have for you all today. It discusses independence and conditional probability, but also talks about some of the other stuff we did with disjoint events. So we're going to have that the probability of the first event A is equal to 1/3. The probability of B is 1/4. The probability of C is 1/5. And then we're going to find the probability of A union B union C under the following assumptions. The first assumption is that all of the events are mutually exclusive, and the second assumption is that all the events are independent. So there's two steps to this problem. First, find A union B union C if they're mutually exclusive, and then find it if they are independent. Okay? Good luck. We'll go over the answer in the next video. See you all then.